That's not a question off of this homework. What questions do you have off of this homework?
None.
So we have no questions about how to identify these values, what type of sequence it is, or how to write the equation.
Yep.
Because I need you to understand something very clearly. The priority of the test that we'll have after Thanksgiving break will be on writing these equations. So we have no questions about that. Yes, ma'am.
F of n just means like, F is just there, and then n is just first, second, third, fourth, fifth.
Well, it's not just that it's just there. F of n, well, n is the input. F of n is what I get out when I plug that input in, right? So if I were to look at f of 1, that means if I plug 1 into the function, I'm getting out 66. So f of n is the output for that particular input. And so like the output for whatever n is this expression.
And you put f when it's recursive or
Well, both of them actually use f of n. You put, it can be either one. We use n when it's a sequence typically, and we use x when it's a continuous function. Well, remember, sequences are discrete. Those other types of functions are continuous. But it's f of n equals an expression like that where there's just an input when it's explicit. When it's recursive, it's f of n equals f of n minus 1, and because that's whatever is the previous output, and you indicate what you're doing to that previous output. That's the idea of recursive. Okay? All right, any other questions before we move on? Okay, any questions about these before we move on? Going once, going twice, sold. All right, so here's the agenda. We're going to do a couple more exponent rules review, and then we're going to look at our objectives before we get back to 2.4, the in-betweeners. So really quickly, I want to talk about 17 and 18, because yes, Caroline, there's going to be a handful of questions over Thanksgiving break. It is going to be no more than it normally is on any normal night.
Good.
So it's barely any at all. Okay?
So I can get it done.
You could probably get it done within like 10, 15 minutes is what it's designed to be.
Well, we got homework.
10 to 15 minutes
Really?
over Thanksgiving break.
Oh.
I'll be honest, I planned on there not being any homework, but because we goofed around earlier this week, we got a whole day behind. Sir?
You mean like just one little bitty thing over a day or actual everyday things?
One normal night of homework
Okay.
over the entire week.
Oh, right.
Those-
It's not, yeah, it's,
I
I
thought-
thought you were saying everything.
no, I'm saying like 17 and 18, and then there's like 3 or 4 more that, and that's gonna be it.
I got scared a little bit.
No. Positive exponents. So, some people may look at 17 and be a little freaked out by it, but all you need to know is this. When we have a positive exponent, what does a positive exponent really mean?
It's multiplying by positive.
I mean, if I have negative 3 to the 5th, I'm still going to be multiplying by a negative 3. What does a positive exponent tell me to repeatedly do, though?
Multiply.
Multiply. That's just going to be negative 3 times itself 5 times. Does that make sense? Now, what I want to do is take a second and talk about a slightly different understanding, though, because it's going to help us understand negative exponents and an exponent of 0 really quickly. A better way to understand a positive exponent, and I would write this down because this will help you with this homework and it'll help you with other things later on.
What page are you on?
And this is on the very back. Okay? So again, it might be helpful to have a writing utensil out and picked up in our hands and ready to write. Caroline. Mask up over the nose as well, please. McKay, same deal. I know that we're tired of wearing masks. I am tired as well. However, we're doing the best with what we got to do our whatever we can to try to help keep people safe. Okay? So 2 to the 3rd. I know it's going to be a little bit different than what you're probably used to writing with this, but a really great thing to understand is when you have, we usually say, hey, it's repeated multiplication, right? And so we just say, hey, it's 2 times 2 times 2. However, a slightly better way to write this is to start at the number 1 and then multiply by 2 3 times, right? Because you need something that you're multiplying those 3 2's by. And this works really nicely when I get to here. 2 squared is 1 times 2 times 2. 2 to the first, right? Because we say we're multiplying by 2 one time. Well, what are we multiplying that 1 2 by? By that 1. Okay? And this is really powerful when we move to 2 to the 0. What am I still starting with?
1,
1. But how many 2's am I multiplying by it?
0.
0, right? I just don't have any 2's there. It's not that I'm multiplying by 0, I'm just multiplying by 0 2's.
So it'd be 1.
Wait, where's the one from?
Wasn't I doing 1 times 2 times 2 times 2? 1 times 2 times 2? 1 times 2? And so it's still a 1.
But where'd you originally get the one?
So the language that we usually use, and this is good right here as well, we say that a positive exponent is repeated multiplication, right? So we're multiplying by how many 2's? 1 2. What are you multiplying that 1 2 by? 1. So it's an understood 1 that's here, and we usually don't write it out, but it's really powerful to understand that because that explains why 2 to the 0 is 1. 2 to the first is 1 times 1 2. 2 to the second is 1 times 2 2's, right? So 2 to the 0 is 1 times no 2, so it's just 1. And this is also really powerful when we get into negative exponents. Does anyone remember what a negative exponent tells me to do?
Multiply backwards
Okay, what would be multiplying backwards?
into the negative.
Division?
Not division. Wouldn't the inverse of multiplication be division?
Sure.
So again, what number am I going to start at though?
1.
And then I'm going to divide by how many 2's?
Negative 1, 2.
1 2, not negative 1 2. Remember that negative exponent purely tells me to divide.
So negative 1 is 1 on 2 negative 1?
What?
I don't know.
No. Gavin, 2 to the first is we're starting at 1 and we're multiplying by 1 2.
Okay.
2 to the negative 1, I'm still starting at 1, but that negative exponent is telling me to divide by 2.
Okay.
2 to the negative 2, what number am I starting at?
1.
1, and then the negative exponent tells me to divide
4.
by how many 2's?
2.
Now notice I'm multiplying the denominator because I'm dividing by both of them.
So it's 4.
So then 2 to the negative 3,
1 over, we're divided by 2 times 2 times
and that explains why you get the answers that you will. If you plug 2 to the negative 3 into the calculator, you get 1/8, or 0.125. Well, so this idea of that 1 being there is actually a really important idea, and I would make this note of this progression because it helps us understand what might be happening in number 17, and we should be able to apply that idea to number 18 as well. What are you confused by?
No.
Okay. Did you get these answers when you plugged it in? Yeah. So please understand, because what Gavin and McKay were saying earlier, that idea of thinking that a negative exponent is going to give us a negative is probably the most common mistake that students make. We need to understand that a positive exponent is repeated multiplication starting at 1, whereas a negative exponent is repeated division starting at 1, right? So we want to recognize those properties, and they're going to be important later. So where it is, there it is. So the note I would make to myself here, right? Positive exponent starting at 1, repeatedly multiplied by the base. But here with a negative exponent starting at 1, repeatedly divide by the base. So that should help you with those two problems over the break. Okay? If you're still writing that down, continue that. I'm going to talk about these objectives really quickly, or remind ourselves. Caroline, can you read our first objective for us today?
I can identify the common factor necessary. How do you say that?
Necessary?
Oh my god, I couldn't say that for finding outputs of an exponential function and inputs of fractional.
So remember, we started yesterday looking at, what's his name? We'll come back to those objectives in a second. Travis's idea, where he said, hey, we're going to average each of those outputs, right? However, we ran into some issues. So we're trying to look at this idea of how are we going to find the outputs for an exponential function even when those inputs are fractional. We can't just average those things, and we'll talk about that in a second. And then the ultimate goal out of this, and we're going to get to this over the next few lessons, is we want to connect radicals to rational exponents. And so rational just means ratio, which a fraction is a ratio of two whole numbers. Right? So we're going to kind of look at that today. So we had f of x equals 4 times 2 to the x. Why do I know that this function is exponential? Why does it have this curve here? So it's not just multiplying, it is, when you say multiplying, what do you mean? There's another word in front of multiplying. Starts with an R.
Recursive.
Not recursive.
Radical.
Not radical.
Ratio.
Racism.
Is it just multiplying once?
Repeatedly.
Thank you, it's repeatedly multiplying. Cheyenne and Donovan, keep your mask up, please. We're repeatedly multiplying by 2, right? So that's an important detail here. It's that repeated multiplication that's going to give it this smooth curve and create that exponential shape. However, when we looked at Travis's idea of just averaging those numbers, we see it right here. It's not a sharp curve. What is this creating in between each of these points? A linear relationship, right? If we just average, remember an average is an arithmetic mean. That was 1.9. Right? But this is exponential, so we don't want arithmetic means, we want geometric means, right? An exponential function, a function with a common ratio, or what was another word we started using here? A common factor, right? A function with a common factor, not a common difference. A common factor is what we should be looking at here. And so now, we talked about that yesterday, we ended up on this idea of commenting on Travis's idea. How does it compare to the table generated in problem 1? It doesn't line up very well, because I need those common factors, not those common differences. So now we're picking up with Miriam. Alright? Cheyenne, can you read us what Miriam suggests, or starting at Miriam suggests? I think it's on the second page, maybe.
Miriam suggests they should fill in the data in the table in the following way. I noticed that the function increases by the same factor each time x goes up by 1. And I think this is like what we did in geometric means. It seems like this property should hold over a half interval as well.
Okay, so it should hold after a half interval as well. Notice this is what she's saying. Every time the x increases by 1, are we multiplying by the same factor? Is that true? Yeah. So her argument is that this property should hold over each half interval as well. So fill in the parts of the table below that you've already computed in problem 1, and then decide how you might use Miriam's new strategy to fill in the missing data. Alright? As in the table in problem 1, each entry should be multiplied by some constant factor to get the next entry. And that factor should produce the same results as those already recorded in the table. Use this constant factor to complete the table. Now, here's something I want you to clearly understand about this constant factor. What do you do with factors? You're multiplying with them, right? However, and so there is a very effective strategy that we learned about with 1.10 geometric means. We talked about it yesterday. However, if you don't remember what that strategy is, could you guess and check to find the factor that would get you from 4 to 8.
Yes, you can.
You can, right? And so I should not see anyone just sitting there doing nothing today. We all have something that we can do. If you cannot remember this strategy, right? You have a small group with you. Talk it out to see if you can remember the strategy. But if you can't, at least guess and check. All right, we ready to get started? Got about 15 minutes to knock out as much of this as we can. Maybe 15 to 20, depending on how much time we have left. Let's get to work.